Welcome to The Explainer. Today we're going to dig into a really fundamental question about something we see absolutely everywhere, from the ocean all the way to the light from stars. What exactly is a wave? Okay, so let's just start with a simple thought experiment. When you see a wave, like this one, moving through a slinky, what do you think is actually traveling from one end to the other? Is it the ripple itself? You know, the actual shape that you can see moving through space? Or is it the slinky itself? Are the individual bits and pieces actually journeying all the way down the line? All right, let's really dive into this because the answer is probably not what you're thinking. If you look really closely at any single point on that slinky, you'll see it's just kind of moving back and forth, or maybe up and down. It actually ends up right back where it started. The particles themselves, they aren't traveling the distance at all. And this brings us to the absolute key idea here. A wave is a disturbance that transfers energy, not the actual material, the matter that it's traveling through. So if it's the energy that's on the move, how does that really work? Well, you can think of it like a chain reaction. It works just like this. Some initial force creates a disturbance. That disturbance then passes its energy to the very next particle in line, which then bumps into the next one, and so on and so on. But here's the thing. Each particle just moves a tiny bit before going right back home to where it started. Now that we've got a handle on what a wave is, it turns out we can classify pretty much every wave in the entire universe just by asking two super simple questions. First question, does it need stuff to travel through? We call these mechanical waves. Things like sound, they need a medium like air or water to move. But then you have non-mechanical waves, like light. They're totally different. They can transfer energy right through the empty vacuum of space. And the second question is, how does that stuff actually move? In what we call transverse waves, the particles move up and down, perpendicular to the wave's direction. Think of fans doing the wave in a stadium. But in longitudinal waves, the particles just compress and expand, back and forth, parallel to the wave's direction, kind of like an inchworm. Okay, so let's use these two rules and see if we can categorize some of the most common waves all around us: sound, light, and water. Right. Sound, it definitely needs air to travel, and it works by compressing all those air particles. So that makes it a mechanical longitudinal wave. Simple as that. What about light? Well, we know it can travel through the vacuum of space, and its waves oscillate perpendicularly, so it's a non-mechanical transverse wave. And finally, water waves. They're mechanical for sure, since they obviously require water to travel, and because we see the water moving up and down, we can go ahead and classify them as transverse waves. And what's so amazing about this whole thing is that this one simple concept, just a transfer of energy, it helps explain some of the most fundamental things happening in our universe. So the real takeaway here is that our world is just constantly being crisscrossed by all these invisible transfers of energy. And, that leaves us with one final question. If so much of what we experience every day is just energy in motion, what other invisible waves might be shaping your world right at this very moment?